next speaker is Ornella. She will talk about hepatitis.
I think I will go to without mic. It's okay? Can you hear me? Yeah? Okay. Hi everyone. My name is Ornella Moro. I'm a PhD student at the University of Roma Sapienza, but actually my PhD is in collaboration with the Food Safety Department of the Italian National Health Institute. So I mainly deal with infectious diseases. Very cool stuff in these times, so in these days. So, but actually, I deal mainly with foodborne zoonosis, that are infections transmitted by food consumption of animal origin, contaminated food, of course, like, for example, salmonella or mad cow, stuff like that. So, okay, the main part of my PhD is about hepatitis E. These are emerging diseases. Yeah, today I'm just telling you a bit about my project and our solution to deal with this disease. Yes.
Wait a moment, sorry.
That's okay. So my talk is really about something really applied. So. Okay.
Can you try again? Does it work?
Okay, perfect, thank you. So I'm trying not to be too bored for you. Some introduction. So hepatitis E is transmitted by a virus. And as all the viruses is a kind of a parasite of other living cells. So of course it needs living organisms to survive and to grow. But it's really difficult to assess once isolated if it's still vital. So it seems, we have no clues about its survival, for example, in the environment after some time, or after treatments like cooking, that for food is important, or use of detergent or stuff like that. It affects human, but of course also several animal species. That is what we are interested in. We are interested in these two subgroups that are shared between humans and several animals like pigs, sheep, deers, and so on. The transmission is mainly oro-fecal. This means that you have to get in contact with infected fecal material, but in industrialized countries not so common. It's usually foodborne. And the majority of cases are caused by the consumption of meat of pigs and wild boars that are the main reservoir for the pathogen. But of course, through fecal contamination, it's possible to contaminate also water, both wastewater, of course, but also surface water. And this means that it's possible to contaminate also like shellfish, there's seafood, and vegetables that could also be vehicle for the virus. The majority of cases is asymptomatic. You can have some mild symptoms or more severe cases in case of in presence of underlying conditions, immunodepression, or of course a very bad liver. But the immunization after the exposure to the pathogen is lasts long life, or it seems so. And we see no symptoms at all in animals. So it's actually not a very dangerous disease, not a very bad disease. But it's an avoidable burden for the healthcare system, and I think we've learned that it's something not so, so it's important. The number of cases increased a lot in the last 15 years, in particular starting from 2010. And the cases increased, although we have a surveillance that is very scattered and messy around a European country. So, of course, our goal is to reduce the circulation of the virus along the whole production chain, and in particular, the transmission to humans. And to do that, we wanted to model the circulation of the virus along the three main compartments of the production chain, so the farm, the slaughterhouse, and the processing plants, and the consumer phase, the retail and consumer. So today, I'm just talking about the first and the last part. So for the farm, we wanted to estimate the number of infected animals entering in slaughterhouse, or the proportion, but yeah. So we looked at the structure of the farm, of an average farm in Italy, because as you know, in Italy we are kind of obsessed with food. So we have a very heterogeneous production and very heterogeneous farming type. But an average farm, it's like this one. So we have a reproduction branch, of course, where sows give birth to piglets that remains with their mother for about 4 weeks. Then they are usually collected all together for other 4 weeks in the weaning phase. And they are subdivided in smaller population into pens that are usually more or less isolated between them for about 5 months. And then they are sent to slaughter. So they live like 6-7 months. Not too exciting as a life. So we choose to use an SIR model that, for all of you who are not familiar with it, it's an approach where we divided the population into 3 main compartments based on the health state. So we have susceptible, infected, and recovered. And we define the infection dynamics that determines the migration from the S compartment to the I compartment, and the recovery dynamics that defines the migration from the I to the R compartment. So we have 2 flows here, the health state flows and the growing of the animal, so the migration from the first to the last, to the second age class. We are not considering the reproduction branch because piglets are usually covered with maternal antibodies, and that branch is usually isolated from the rest of the farm, so it does not affect the infection dynamics. So these are the general parameters of the model. We looked at time in days, so we have discrete time. We take account of the day post-infection, so the time, the day spent in the infected compartment. S and R are, of course, the number of animals susceptible and recovered, and I, the infected, and then that depends on A. IC is the total number of contagious animals. So we are considering a latent period of 3 days, and the other 2 are not so important. So for the infection dynamic, we used a Poisson process. So the newly infected animals at the end of a day are Poisson distributed with parameter Qt times S, where Qt is the probability to have an actual infective contact in a day, at least one, and where, of course, also the actual infective contacts in the day are Poisson distributed, depending on the mean number of contacts per day, on the proportion of contagious animal in the area, and on the probability to develop infection given a contact with an infected animal, a contagious animal, actually. For the recovery, we built a recovery probability depending on the days spent in the infected compartment. And we used just a binomial over the infected animals for 8 days with probability QA, and we sum up them to have the total number. So these are the equations. I'm not going into details with them, but just it's basically a Markov chain. So we have for each compartment the baseline from the day before, one inflow, or from the previous age class, or from the previous health state compartment, and 2 outflows, one towards the next health state compartment, then becomes an inflow in the next health state compartment, and an outflow towards the next age class that becomes an inflow here. So, for the consumer level, we wanted to estimate again the number of infected individuals in Italian population, susceptible population, but for specific food items consumed in a year. So the items are the ones that I more or less explained with something more, but basically at that one. So we started looking at the data describing the presence of virus in food in Italy. And we built, starting with them, a probability distribution for the concentration of virus in an average portion of food belonging to these categories. Then we built an infective threshold, individual threshold, meaning a probability distribution that describes the probability to develop infection given the ingestion of a specific amount of virus. And using these two probabilities, these two distribution, we calculated the probability to develop infection after one single meal, has the probability that in that specific meal the concentration of virus exceeded the personal threshold, of course. And we use it to build a geometrical distribution that modeled the first successful infection, where of course the trials are the different meals in a year. And estimating the number of portions consumed in a year, the average number of portions consumed, we got the probability to develop infection in a year, and then we sum up over the susceptible population to get the average of the binomial, to get the average number of infected. So that was basically it. It was just a little journey. So we are working on the remaining part to link the production chain to plan some intervention. And we are working also on wild birds because the supply is very different for wild birds. It's more connected to local production, local butcher and hunters and stuff like that. And we'd like to include also regional stratification to catch better the differences in consumption habits and farming type also. So this was it. Thank you very much.
Thank you very much for the very interesting talk. Are there any questions? Yes, Nasty?
Maybe just a question. How much data do you have?
That's a crucial point. We started from data to know how to build the model, because data are really not so much. In particular, consumption data are really difficult to find and to collect. They are totally ununderstandable. They are totally messy. So it's a crucial point, actually. We have not much data.
Was there another question? You were not writing that, sorry.
I have a similar question. You just said on the previous slide, on slide 19, you will improve the model also including the slaughterhouse, and I can't read the yes, the white one I can read, the orange one I can't read. The processing plant, yes. So you want to increase those, but how will you check if that's even needed when when it's hard to check, now you're going from farm to consumer, and you can't validate some more. Do you have enough data to really validate?
Actually,
so I'm my question is you want to make the model more complicated. Can you show that this is needed?
Actually, the idea is that when we have the entire production chain, we can cross-validate using the data that we have to improve our parameters. So actually, we think that it's better to add the lacking part to be able to cross all the data that we have to tune the parameter the best.
Thanks.
Thank you.
Any other question?
Maybe just a curiosity. Is there any, so perhaps you have lots of pigs in small spaces, then they go to open spaces, or maybe that you model the, I don't know, maybe not the slaughterhouse, but other type of places where you have a lot of spatiality. There's space. Because it's really, doesn't make a big difference. It doesn't make sense to include it somehow.
Yeah, absolutely. But it's difficult to understand where the farm types are, because in the North Italy, usually they are intensive, kind of like farming. So the pigs don't go around. They are just stuck in their areas. But like in Center and South Italy, they have like mixed farming type where pigs go out and in. So yeah, we are of course, thinking on how to catch all the differences because we think that it matters. That the contact between pigs, but also between, for example, pigs and wild boars. So the biosecurity, the possibility to have stuff coming in and out, it's something that matters for the infection dynamics. If that was your question.
Yeah, perfectly. So it would be nice to be able to argue that they should have larger spaces, not only because their lives would be less terrible, but also because it will reduce the infection rates. And so you would spend less state money treating disease.
It's actually, I'm not so sure. Probably the intensive ones are more more safe. The pigs are they have less space, but they kind of do all the infective curves. So when they enter to slaughterhouse, they are usually all immune. We have like a seroprevalence of 95% in farms, so they are immune. But if they are very scattered, maybe the dynamics is lower. It's possible the dynamics is low, so it's kind of different. So.
I see. Thanks.
Okay. Thank you.
Thanks again to the speaker.